In the spring of 1943, a damaged Republic P-47 Thunderbolt made an emergency landing in German-occupied France. The pilot was captured, but what the Germans found inside that aircraft would become one of the most sobering technical revelations of the entire war. When Luftwaffe engineers finally got their hands on the Pratt Whitney R-2800 Double Wasp engine, their detailed analysis revealed a technological gap so profound that it would fundamentally alter German perceptions of American industrial capability. The P-47 Thunderbolt was already known to German pilots as a formidable opponent. Weighing in at over 7 tons when fully loaded, it was the heaviest single-engine fighter of World War II. But weight wasn't a weakness. It was a feature. That mass was driven by an engine that produced power levels German engineers had only theorized about. The discovery. The captured P-47 was transported to the Luftwaffe testing facility at Rechlin, northeast of Berlin. This wasn't the first American aircraft the Germans had examined, but it was the first time they could thoroughly analyze a frontline P-47D model in relatively intact condition. Previous encounters had yielded only wreckage or older variants. The technical commission assigned to examine the aircraft was led by experienced Luftwaffe engineers who had spent years developing Germany's own fighter engines. These weren't novices impressed by foreign technology out of ignorance. They were experts who immediately recognized they were looking at something extraordinary. The R-2800 Double Wasp was an 18-cylinder, twin-row radial engine displacing 2,800 cubic inches. At maximum war emergency power with water injection, it produced 2,535 horsepower. To put this in perspective, Germany's most powerful operational fighter engine at the time, the BMW 801 that powered the Focke-Wulf FW-190, produced 1,700 horsepower under similar conditions. The American engine was generating nearly 50% more power. But raw horsepower numbers only told part of the story. What truly shocked the German engineers was how the Americans achieved this power level and, more importantly, how they did it reliably. The engineering marvel. German technical reports from Rechlin, some of which survived the war in captured Luftwaffe archives, reveal the extent of their analysis. The engineers didn't just measure the engine. They disassembled it completely, examined metallurgy, tested individual components, and attempted to reverse engineer the manufacturing processes. The R-2800's construction revealed manufacturing techniques that were simply beyond German industrial capability in 1943. The engine used precision-forged aluminum alloy parts with tolerances that German factories couldn't maintain at scale. Each cylinder was individually machined to specifications that required quality control measures Germany didn't have the resources to implement across mass production. One Luftwaffe report noted with frustration that the connecting rods alone represented a manufacturing achievement Germany couldn't replicate. These rods had to withstand enormous stresses while maintaining precise weight matching across all 18 cylinders. The Americans were producing these components by the thousands with consistent quality. German factories struggled to produce even their existing engine components with the required precision, and their reject rates were significantly higher. The supercharger system particularly impressed the German analysts. The R-2800 used a two-stage, two-speed mechanical supercharger with an intercooler system that maintained performance at high altitudes. German engineers had been working on similar systems, but the American implementation was more advanced and, crucially, more reliable. The intercooler design was especially noteworthy. Compressed air from the first supercharger stage passed through a heat exchanger before entering the second stage, significantly improving efficiency and allowing higher boost pressures without detonation. The German report specifically mentioned that this system was exceptionally well designed and represented a level of engineering integration we have not achieved. But perhaps most significant was the engine's reliability. The Germans tested the captured R-2800 extensively, running it through various power settings and conditions. What they found was an engine that could operate at maximum power for extended periods without failure. This was something German engines could not do reliably. The metallurgical gap. When German metallurgists analyzed the materials used in the R-2800, they encountered another sobering reality. The Americans were using high-grade aluminum alloys and specialized steels that Germany either couldn't produce or couldn't produce in sufficient quantities. By 1943, Germany was facing severe shortages of alloying elements critical for high-performance engine production. Nickel, chromium, molybdenum, and other strategic materials were increasingly scarce. The Allied naval blockade and the loss of foreign sources meant German engineers were forced to develop substitute materials that inevitably resulted in inferior performance and reduced reliability. The R-2800 cylinder heads, for example, used an aluminum alloy that could withstand higher temperatures and pressures than comparable German materials. The valve springs were made from special steel alloys that maintained their properties under extreme heat. Even the spark plugs represented superior materials engineering. A particularly telling detail from the German analysis concerned the engine's crankshaft. This massive forged steel component had to be perfectly balanced and capable of withstanding the enormous rotating forces generated by 18 pistons firing in sequence. The German report noted that producing such a component required forging equipment and metallurgical expertise that exceeds our current manufacturing capability. The Americans were also using superior lubricating oils. The synthetic and semi-synthetic lubricants found in the captured aircraft allowed the engine to operate at higher temperatures and maintain their properties better than German equivalents. This wasn't a minor detail. Engine oil technology was critical to reliability, and the Americans had a significant advantage. German engine development. A different path. To understand why the Germans couldn't match the R-2800, we need to examine their own engine development philosophy and the constraints they faced. German aero-engine development had followed a different trajectory than American efforts. While the Americans had invested heavily in large radial engines for commercial aviation throughout the 1930s, the Germans had focused primarily on inverted V12 liquid-cooled engines like the Daimler-Benz DB601 and Junkers Jumo 211. These engines had their own advantages. They were more aerodynamic when installed in fighters, produced less drag, and in the hands of skilled pilots, aircraft equipped with them could be extremely effective. The Messerschmitt Bf 109, powered by various versions of the DB601 and later DB605, was a formidable fighter throughout the war. But by 1943, the limitations of German engine technology were becoming apparent. The DB605, which powered late-model Bf 109s, produced around 1,475 horsepower at maximum output. Even with boost systems like the MW50 methanol water injection, it rarely exceeded 1,800 horsepower, and this came at the cost of reduced engine life. The BMW 801 Radial, which powered the FW190, was Germany's most powerful operational fighter engine and the closest equivalent to the R-2800. But even in its most advanced variants, it produced significantly less power. The BMW 801D2 generated 1,700 horsepower with MW50 injection, still well short of the R-2800's output. German engineers were certainly capable. They understood the principles of high-output engine design. But understanding and implementation are two different things. The Germans faced multiple constraints that prevented them from matching American achievements. First was the manufacturing constraint. German industrial production, while impressive in many ways, couldn't match American mass production capabilities. The United States produced over 125,000 R-2800 engines during the war. This massive production run allowed for continuous refinement, improvement, and cost reduction. German engine production was smaller scale and more fragmented among different manufacturers. Second was the resource constraint. By 1943, Germany was fighting a multi-front war and facing increasing resource shortages. Strategic materials needed for advanced engine production were being diverted to other priorities, or simply weren't available in sufficient quantities. The Americans, protected by oceans and with access to global resources, faced no such limitations. Third was the development time constraint. The R-2800 had first run in 1937 and entered production in 1939. By the time the Germans captured one in 1943, Pratt Whitney had 6 years of continuous development and refinement. The engine that German engineers examined wasn't a new design. It was a mature, proven power plant that had gone through multiple iterations of improvement. The attempts to respond. The German response to discovering the R-2800's capabilities was predictable. They accelerated development of more powerful engines. But by 1943, it was already too late to bridge the gap. Several German projects aimed to produce engines in the 2,000-plus horsepower range. The Daimler-Benz DB603, a larger version of the DB601, was developed with various supercharger configurations. The DB603E variant produced around 1,800 horsepower, getting closer to American levels, but still falling short and suffering from reliability issues. The Junkers Jumo 213 was another attempt to increase power output. This inverted V12 engine eventually produced around 2,000 horsepower in its most advanced variants with MW50 injection. But development was slow, and production difficulties meant it never equipped German fighters in large numbers until very late in the war. BMW worked on more powerful radial engines, including the BMW 801E and the BMW 801F, which aimed for 2,000 horsepower. These projects faced repeated delays due to cooling problems, manufacturing difficulties, and resource shortages. The BMW 801F never entered production. Perhaps the most ambitious German response was the development of the Daimler-Benz DB613, a 24-cylinder X-configuration engine formed by coupling two DB605s. This engine theoretically produced over 2,500 horsepower, matching the R-2800's output. But it was enormously complex, heavy, and never progressed beyond the testing phase. The manufacturing challenges were insurmountable given Germany's situation by 1944. There were also turbocharged and turbo-compound engine projects. The Daimler-Benz DB605T with turbocharger showed promise for high-altitude performance, but turbocharger development had been neglected in the pre-war years, and catching up proved difficult. The Americans had been developing turbocharger technology since the 1920s, and by World War II, they had a commanding lead. Every German attempt to match American engine performance ran into the same fundamental problems: insufficient manufacturing capability, material shortages, and lack of development time. Even when German engineers designed engines that theoretically matched American specifications on paper, translating those designs into reliable, mass-produced reality proved impossible. The broader implications. The German examination of the R-2800 engine represented more than just a technical assessment of one enemy aircraft component. It forced a reassessment of American industrial and engineering capabilities that German leadership had consistently underestimated. Nazi propaganda had long portrayed Americans as industrially capable but technologically inferior. The cultural prejudices of German leadership led them to believe American engineering couldn't match German expertise. Captured equipment from the early war years seemed to support this view. American tanks, for instance, were initially inferior to German designs. But the P-47's engine told a different story. This wasn't crude mass production overcoming quality with quantity. This was sophisticated, advanced engineering implemented at massive scale. The Americans had achieved what the Germans considered nearly impossible, combining cutting-edge performance with reliable mass production. German intelligence reports from 1943 onward show a marked shift in tone regarding American technical capabilities. The previous dismissive attitude was replaced by genuine concern. If the Americans could produce engines like the R-2800 by the tens of thousands, what else were they capable of? The psychological impact on Luftwaffe pilots, who flew captured P-47's, was equally significant. Test pilots at Rechlin flew the Thunderbolt against German fighters in mock combat. Their reports praised its high-altitude performance, diving speed, and especially its ability to absorb damage and keep flying. One test pilot noted that the P-47 could sustain combat damage that would destroy any German fighter and still return to base. This durability was directly related to the R-2800's reliability and power. The massive engine could take hits and continue operating. It could lose cylinders and still produce enough power to fly. German engines, built to tighter tolerances and with less robust materials, were far more vulnerable to combat damage. The production numbers tell the story. The scale of American engine production revealed by post-war analysis is staggering. Pratt Whitney didn't just build R-2800 engines at one facility. They constructed multiple dedicated production plants across the United States, each capable of producing thousands of engines annually. From 1940 to 1945, Pratt Whitney produced approximately 125,000 R-2800 engines. This represented an average of over 2,000 engines per month, sustained for 5 years. Peak production reached over 4,000 engines per month in 1944. To put this in perspective, Germany's total production of all fighter engines combined was around 90,000 units for the entire war. The Americans produced more of a single engine type than Germany produced of all types combined. But quantity alone doesn't capture the full picture. The R-2800 engines rolling off American production lines in 1945 were significantly better than those produced in 1941. Continuous refinement improved reliability, increased power output, and reduced manufacturing costs. American factories achieved what German industry could not: simultaneous improvement in quality and increase in quantity. The production of R-2800 engines also drove broader industrial capabilities. The precision machining equipment, quality control systems, and workforce training required to build these engines created infrastructure that benefited all American war production. The Germans, by contrast, struggled to maintain production standards as the war progressed. By 1944, German engine quality was declining due to material substitutions, hastily trained workers replacing skilled craftsmen, and Allied bombing disrupting supply chains. American engine quality was improving for the opposite reasons: better materials, more experienced workers, and completely protected industrial infrastructure. What could Germany have done differently? This question haunted German aviation engineers after the war. Could different decisions in the 1930s have prevented this technological gap? The answer is complex. Some historians argue that German focus on liquid-cooled V-12 engines was a strategic mistake. Radial engines like the R-2800 were inherently more durable and could scale to higher power outputs. Had Germany invested more heavily in radial engine development in the 1930s, they might have been better positioned. But this argument overlooks important context. Radial engines were larger, heavier, and created more drag. For the fighter designs Germany prioritized in the late 1930s, liquid-cooled engines made sense. The Bf-109's slim profile and resulting aerodynamic efficiency came from using a compact inline engine. A radial engine would have required a complete redesign. More fundamentally, Germany couldn't have matched American production capacity regardless of engine type. The United States had a larger industrial base, more raw materials, better access to strategic resources, and complete protection from strategic bombing. Even if German engines had been technically equivalent to American designs, they couldn't have been produced in equivalent numbers. The real German mistake was strategic, not technical. Going to war with the industrial capacity of the United States arrayed against them was a miscalculation from which no amount of engineering excellence could recover. By the time German engineers examined that captured R-2800 in 1943, the outcome was already determined. They were analyzing the evidence of their inevitable defeat. The legacy. The R-2800 Double Wasp continued to power aircraft long after World War II ended. It remained in production until 1960, with total production exceeding 125,000 units. Post-war versions powered aircraft like the Douglas A-1 Skyraider, which served into the Vietnam War, and various civilian aircraft. The engine's reliability became legendary. R-2800s accumulated millions of flight hours in military and civilian service. Stories of these engines bringing damaged aircraft home on a handful of functioning cylinders were common. This reliability stemmed from the robust design and quality manufacturing that German engineers had identified in their 1943 analysis. For German engineers who survived the war, the R-2800 represented a humbling lesson. Those who went to work for the Americans in the post-war period, contributing to projects like the X-15 rocket plane and early space efforts, often reflected on how the examination of captured American equipment had revealed the limitations of their own wartime achievements. The technical reports produced by the Luftwaffe examination of the P-47 and its engine survived in various archives. These documents make fascinating reading today. They're written in the precise, technical language of engineering analysis, but underneath the professional tone, there's an unmistakable thread of respect bordering on awe. One report concluded with a remarkably candid assessment. The Pratt Whitney R-2800 represents an achievement in aero-engine design and production that we cannot match with our current resources and capabilities. The Americans have solved problems we are still struggling with, and they have done so at a scale of production we cannot approach. Technical specifications in context. Let's examine some specific technical comparisons that illustrate the gap German engineers confronted. The R-2800's bore and stroke dimensions were 5.75 inches by 6 inches, creating a displacement of 2,804 cubic inches. This large displacement provided the foundation for high power output. By comparison, the BMW 801's displacement was 2,560 cubic inches, already large for a German radial, yet still smaller than the American engine. But displacement alone doesn't determine power output. The R-2800 achieved high specific power output, horsepower per cubic inch of displacement, through several features. The two-stage supercharger maintained high manifold pressure at altitude. The intercooler reduced inlet air temperature, allowing higher boost without detonation. The robust construction allowed sustained operation at high power settings. The compression ratio of the R-2800 was 6.7 to 1, relatively modest by modern standards, but appropriate for the 100-octane fuel it was designed to use. German engines often used higher compression ratios, but they were limited by lower-octane fuel availability. By 1943, Germany was experiencing severe aviation fuel shortages and quality issues. Fuel quality was another area where Germany couldn't compete. American 100-octane aviation gasoline had excellent anti-knock properties, allowing higher manifold pressures and more aggressive ignition timing. German aviation fuel varied in quality and octane rating, forcing conservative engine tuning to avoid detonation. The R-2800's valve train used pushrods and rocker arms, a simpler system than the overhead camshaft designs used in some German engines. But simplicity proved advantageous for reliability and ease of maintenance. The American system had fewer components to fail and could be serviced more easily in field conditions. Cooling was achieved through a combination of cylinder fins and high airflow. The P-47's large cowling and efficient ducting ensured adequate cooling even during prolonged climbs at high power. German radial engines, particularly the BMW 801, struggled with cooling problems that limited sustained high-power operation. The R-2800's ignition system used dual magnetos with 2 spark plugs per cylinder, providing redundancy and more complete combustion. Each magneto was capable of keeping the engine running if the other failed. This redundancy was typical of American engine design philosophy: build in safety margins and backup systems. Engine weight was often cited by German analysts. The R-2800 weighed approximately 2,350 pounds dry, considerably heavier than comparable German engines. But this weight included robust construction that contributed to reliability. German engines achieved lighter weight partly through more fragile construction. The power-to-weight ratio still favored the R-2800 when considering its higher output. At maximum power, the R-2800 produced approximately 1.08 horsepower per pound of engine weight. The BMW 801D2 produced approximately 0.94 horsepower per pound. The American engine was both more powerful and more efficient despite being heavier. Maintenance and field reliability. One aspect that particularly impressed German analysts was the R-2800's maintainability. American engines were designed with field maintenance in mind. Components could be replaced relatively easily, and the engine could be removed and installed with standard equipment available at forward airfields. German engines, by contrast, often required specialized tools and more extensive disassembly for routine maintenance. The inverted configuration of engines like the DB605 made accessing certain components difficult. This wasn't necessarily a design flaw. It was a trade-off made for other advantages, but it did impact operational availability. The R-2800's modular design meant that major components like cylinder assemblies could be replaced individually without complete engine overhaul. This was particularly valuable in combat conditions where quick repairs meant the difference between an aircraft returning to service or remaining grounded. American maintenance documentation was also superior. Detailed technical manuals, comprehensive parts catalogs, and systematic troubleshooting guides ensured that even relatively inexperienced mechanics could maintain the engines effectively. German documentation was often less comprehensive, and the shortage of experienced mechanics as the war progressed compounded maintenance challenges. Time between overhaul, TBO, ratings told another story. The R-2800 had a TBO of around 1,000 hours under normal operating conditions. German fighter engines typically required major overhaul after 100 to 300 hours. This difference meant American engines stayed in service longer and required less industrial capacity devoted to overhaul and rebuilding. The Germans couldn't match these maintenance intervals partly because their engines operated closer to their design limits, and partly because materials quality and manufacturing precision weren't consistent enough to ensure longer service life. The human element. Behind the technical specifications and production numbers were people, the engineers, workers, and pilots on both sides. German engineers examining the R-2800 were highly trained professionals who understood immediately what they were seeing. Their reports reflect professional respect for their American counterparts' achievements, even as they grappled with the implications for their own war effort. Many of these German engineers had dedicated their careers to advancing aero-engine technology. Some had worked on record-breaking aircraft in the 1930s. They weren't incompetent or backward. They were simply operating under constraints that made their task impossible. The American engineers and workers who designed and built the R-2800 represented a different industrial culture. The American approach emphasized standardization, interchangeability, and continuous process improvement. Workers on production lines were encouraged to suggest improvements. Quality control was systematic and rigorous. This cultural difference in manufacturing philosophy was as important as any technical factor. American industry had evolved mass production techniques since the early 20th century. By World War II, these methods were highly refined. German industry, while sophisticated, remained more craft-oriented in many areas. For pilots, the difference was existential. American pilots flying P-47's could push their engines hard, knowing that if they survived the mission, the engine would likely bring them home. German pilots had to manage their engines more carefully, always conscious of the risk of mechanical failure even without combat damage. The final assessment. When German engineers completed their analysis of the captured R-2800 engine in 1943, they produced a comprehensive technical report that circulated among Luftwaffe leadership and German aviation industry officials. The report's conclusions were sobering but accurate. They noted that the American engine represented a level of industrial and engineering achievement that combines theoretical excellence with practical manufacturing capability we currently cannot match. The report specifically identified material quality, manufacturing precision, and production scale as areas where Germany was at a significant disadvantage. Perhaps most significantly, the report concluded that even if Germany could design an equivalent engine, which they believed possible, they lacked the industrial capacity and resources to produce it in meaningful numbers while simultaneously maintaining production of existing engine types. This assessment was prescient. By 1944, German aviation industry was struggling to maintain even current production levels as Allied bombing intensified and resource shortages worsened. New engine development, regardless of technical merit, couldn't overcome these fundamental constraints. The story of German engineers examining the P-47's engine is ultimately a story about the limits of technical expertise when divorced from industrial capacity and resource availability. German engineering excellence was real, but it couldn't overcome the massive material and industrial advantages possessed by the United States. For historians of technology and World War II, this episode illustrates a broader truth. Wars are decided not just by the quality of individual weapons or the courage of individual soldiers, but by industrial capacity, resource availability, and the ability to translate design into mass production. The R-2800 engine was a symbol of American industrial might, and when German engineers examined it in detail, they were confronting the reality of their nation's strategic position. The Germans could analyze the engine, understand its principles, and admire its construction. But they couldn't replicate it, and they couldn't change the fundamental economic and industrial realities that made its production possible. In that sense, the moment German engineers realized they couldn't match the R-2800 was the moment they truly understood how the war would end.